Hey guys, welcome back. Now, I usually do sessions on MuleSoft, but I'm also into Linux, cryptography, ethical hacking concepts, and my personal go to programming language will be C, Python, and shell scripting. So, in today's topic, let's drift sideways and learn something new and useful. We'll learn about symmetric and asymmetric key encryptions, the difference between encryption and hashing. So let's start off with the difference between encryption and hashing. Now, as per the common definition, let me explain the process of encryption and then we'll move ahead to the hashing part. So, encryption is a process of altering a certain useful message to an unreadable gibberish. Here, your unencrypted message doesn't always has to be plain text or a number. So, it's not a compulsion to have a readable format always to encrypt. Sometimes the garbage itself can be gold. So the process of encryption is reversible, where you use an encryption key to alter your original information to a garbage and do the inverse by decryption with decryption key. So encryption is like a two-way function, whereas hashing one-way function. Now our interest to whether use a single key to encrypt and decrypt or not calls the distinction between symmetric and asymmetric key encryptions. The logic using which you perform these operations is called an algorithm. The algorithm makes the process of encryption, decryption working and unique. Now, these are some common algorithms under the symmetric key encryption: AES, blowfish, twofish, etc. Algorithms under asymmetric key encryption are also known as public key encryption algorithms. These are some of the commonly known asymmetric key encryptions are RSA and Diffie-Hellman key exchange. Now in here, I will cover one from each category of the symmetric and asymmetric key encryptions. So I choose to do a practical example on AES, which is a symmetric key encryption algorithm, and RSA, which is the counterpart, public key encryption. Now let me walk through how to encrypt using AES. For my demonstration, I'll be using Git Bash software to use our to do our encryption and decryption. So now Git Bash is a tool which already has OpenSSL module. So I'll be using OpenSSL to demonstrate the encryption and decryption process. So now first, before I begin, I need to talk about the minute difference between symmetric and asymmetric key encryption. In asymmetric key encryption, we have a single key to encrypt and decrypt, but in an asymmetric key, you encrypt with one key and you decrypt entirely with a different key. So, asymmetric is a case where you decrypt it with a private key. The private key is the thing which you would be holding on to yourself, but the public key is something which you'll pass on to the rest of the world for in order to encrypt their information. So, asymmetric encryption is primarily used in HTTPS protocol or widely used in all kinds of internet transactions. Now let's first cd to our new folder which I have created. The folder name of the folder is AES and inside it has a release.jks file. So my intention is to encrypt this .jks file. As I already told before, the information which you're going to encrypt doesn't always has to be a readable text. It can be a gibberish as well. So I can go ahead and encrypt this release.jks file to an encrypted release.js and then later we'll try to decrypt it. So the command to encrypt the release.js file is OpenSSL enc tag v tag no salt tag AES256 CBC, and now you need to pass in your file which you want to encrypt and the output of the encrypted file. You define your encoding method for the key which you pass. So I'm choosing base64 as my key encoder. I pass a tag k which takes in the value of my key. I pass an IV. IV is also called as initialization vector. Now salt and IV are two different strings which gets added to your block size each time and try to make it totally unpredictable. An initialization vector is a value which gets added to your first block, whereas the salt keeps on adding to each block throughout the process of encryption. But in here, I do not wish to use any salt. I'm just going with an initialization vector, and I specify the value for the initialization vector. Now if I go ahead and press enter, it's going to simply create a new file named as encrypted release.jks in the same folder. Now if I want to simply decrypt this, I can specify the tag D right after the env tag v. So the tag D tells the OpenSSL to decrypt the file which you're passing in the in parameter, and then what you'll be getting from the out tag would be your unencrypted release.js file. So while decrypting, you pass in your encrypted JKS as an input and get your unencrypted release file, your original release file, as an output. You pass in the same key in the IV. If you change any one of this key or IV, it's going to simply break and then it will not be able to do the decryption. Now the same process can be done using most of the known familiar websites you are aware of on the internet. So recently we have multiple apps to do the same operation. You can try doing AES encryption in your browser or through a mobile app. All that you should be aware of is whether you're using which specific variant of AES encryption. So here I'm using 256-bit CBC chain block cipher mode to do my encryption and decryption. If you wish to do your encryption with a 128-bit CBC mode, you can simply change the tag AES-128-CBC. So let's demonstrate RSA in similar fashion how we did AES in OpenSSL. To do RSA, public key encryption, there are certain calculations to be performed ahead. RSA is complex. Unlike AES single key encryption and decryption, for RSA, we need to generate two keys, a public key and a private key. A public key to encrypt the information and a private key to undo its effects. So it's our responsibility to generate a public-private key pair first, pass on the public key to the sender of the message. So if a person A wants to receive the message from person B through the internet, since they can't use a symmetric AES key anymore, first the person A asks the sender person B to encrypt his message using the public key of person A. Next, since Mr. A already has a specially generated private key for the public key he shared with B, only Mr. A can decrypt the encrypted text, undoing the effects of the public key. The calculations go way too deep into RSA just to create the public-private relationship. Here are the formulas to create a public-private key pair. So the steps goes as follows. Person A performs these relevant steps before he sends his public key, which is a combination of his public exponent and the public modulus. Step 1. Choose two large prime numbers and multiply both to get n, where n is your public modulus. The prime numbers should not share any common factors. Step 2. Solve the prime factorization of n by finding phi, where phi of n is equals to P1 minus 1 into P2 minus 1. Step 3. Once you found your phi of n, choose a number e, which is your public exponent, which does not share a common factor with phi of n. That's it. These 3 steps will ensure you to create a public modulus, a public exponent, and your phi of n. Now using these 3 parameters, you need to calculate your d, which is your private key. So in order to show an example to support our calculations for these 3 steps, I will choose 73, 79 as our P1 and P2. Both of them are not sharing any common factors between each other. Now calculating n, it would yield us 5767 as our public modulus. Now we need to calculate the phi of n for 5767, which will be 72 into 78, which is equals to 5616. Now I choose the e, the public exponent, as 5, and the divisibility factor k would be 4. This is much easier to guess by yourself once you understand what's happening with the calculations. Now calculating your d is equals to divisibility factor into phi of n plus 1 divided by your public exponent 5. So once you do this calculation, your private key would result 4493. Now let's say a message needs to be transmitted by person B. He wants to send a message which is a number 89. So in order for us to get the number 89 without the whole world saying it, first person B will try to calculate the ciphertext for the value of 89. His calculation goes as follows: 89 to the power of 5 mod 5767. Remember, we already shared E and N, which together makes our public key, to the person B. Now the ciphertext would result out to be 223. Once we receive the ciphertext from person B, we can go ahead and simply decrypt it by doing the below calculation. 223 to the power of 4493 mod 5767, which will result to 89. Hence, we have successfully demonstrated public-private cryptography. Now let's demonstrate and try the same in OpenSSL. Remember, you don't need to go through all these calculations in OpenSSL. The task would be simpler. You don't need to calculate phi of n. You don't need to calculate your divisibility factor. All that you have to choose is caring about a public modulus and public exponent. OpenSSL will take these 2 numbers and try to calculate your phi of n and your private key. Once it generates a private key for a public key, you can use that. You can send the public key to the sender of the message and ask him to encrypt it with the help of that key. Later, you can use the private key, which you already have with you, to decrypt the encrypted message from the sender. Here are some more calculations which I haven't shown, but it would be useful. If you're wondering how did we derive the relation between the private key and phi of n and your public exponent, then here are the necessary steps. Now, RSA is ensured by the time complexity of solving the phi of n for a given n. So it's near to impossible for a hacker to figure out phi of n for the public key e, n, which person A had made visible to the entire world. But the hacker can still trick you by performing a man-in-the-middle attack. That's where you use the concept of SSL certificates and a certificate authority. RSA is primarily the major cryptographic method used in HTTPS transactions. It is the world standard for most of the HTTPS transactions. Now, there are some other HTTPS transactions which are using the Diffie-Hellman key exchange. I kindly advise you to take a look at that as well. Now let's try implementing RSA using OpenSSL. Usually, our character length of P1 and P2 are way too large. So by default, RSA uses 2048 bit length for P1 and P2 and create a public modulus which is around 4096 bit character length. Now you can just imagine, it's near to impossible to find the prime factorization for a 4096 bit public modulus. Now here is a task for you. Take the number 8. Can you tell me how many factors does the number 8 has? It can be 2 into 4, 1 into 8. Now what about the number 16? You can say 2 into 8, 1 into 16, 4 into 4. Now what if I ask for 50? You can say 5 into 10, 50 into 1, 25 into 2. Now if for the number 100, we have 1 into 100, 2 into 50, 4 into 25, 10 into 10, etc. Do you think it's really possible to find the prime factor for 4906 bit character length of value? I guess not. So first, in order to encrypt and decrypt any message, we need to create a key pair, a public-private key pair. To do that, type in OpenSSL gen p key. Gen p key is a short form for generating public key. Type in algorithm, and the algorithm which we'll be using is RSA. Now you mention your public key options. So the syntax for that is p key opt, and here are the options which I would like to use. RSA keygen bits 2048. So I would like to generate a public key with 2048 bits of character length. So that's my first option. I would like to generate one more option. So tag p key opt, and then the second option will be RSA keygen public exponent. So now I'm choosing my public exponent as 5. So I want my key length as 2048 bits and my public exponent as 5. Now I need to output my private key. So for the person A, the private key would be private key a dot pem. .pem is the encryption format, and when we press enter, it has generated our private key. Now you see the private key. This doesn't make much sense because this is in base64 format. This kind of format is widely used to transport your message through the internet in a lighter weight. Now, in order to see the actual text version of this private key, type in OpenSSL p key, your input, which is your private key, .pem, and you want it to be displayed as text. Since I don't want this whole text to be displayed on the screen, I would try to use this pipe operation and limit the number of characters which will be displayed. So if you see here, as usual, we have the private key, which is the base64 text. Now we see the hexadecimal text, the public modulus, the public exponent, which is 5, our private key, and the two different prime numbers which are by default used for this public key encryption. Now I'll come out of this. So now we have just generated our private key. In order to extract the public key out of it, you need to type in OpenSSL p key, input your private key, but instead of using the tag text, this time you will be requesting an output file. So you mention minus out public key of a.pem file, and you say I want the public key out, so pub out. This has generated your public key from the private key. So the first step would be generating a private key where you mention the public key exponent and your key length. The second step is to extract a public key out from the private key. So if you encrypt your information using the public key, the only way to decrypt that information would be using the private key. And this is the key which you do not want to share with anyone else but yourself. Now let's view the content of the public key. So as usual, I would say cat public key a.pem. Now it has the public key in base64 format. This isn't useful. To see it in text format, same as how you did it with the private key, just try to do the same for the public key. So replace the private with public. This is going to show you the public key. So we have the base64 encoding of the public key and the normal text version where you have the modulus and your public exponent. So this is the key which you will be sharing to your sender, and your sender will try to encrypt your information using this key, and later you can decrypt your file using your private key. Now let's try to encrypt a text message using this public key, and then later we'll try to decrypt with the private key. So I will use the cat command to create a message.txt file. In here I'll type in hi, good morning. So this is my text message I would like to encrypt. Now as you can see, it has created a message.txt file on your right. So let's try encrypting this. So the command to encrypt your text file using your public key would be OpenSSL. So first remember that this is an operation which will be done by the person B, your sender. This operation is not done by the actual owner of the private key. So the command would be OpenSSL pkeyutil. So using the public key utility, we'll mention encrypt the file input message.txt, and you're giving a public key as an input, and you mention the input key, your public key name, and you mention your public key file, which is public key of a.pem. Now you want to output your ciphertext, so mention it as tag out and call it as cipher.bin. .bin is a binary format of your ciphertext. Now when you press enter, it's going to create an encrypted binary file of your original message, which is the message in the message.txt. Now in order to decrypt the same file, all that you need to do is reverse the operation. So this is the operation which will be done by the person A, the owner of the private key. So he says OpenSSL pkeyutil tag decrypt tag in. Now instead of, so you need to decrypt your cipher, so mention the name of the file, cipher.bin, and then since you're using a private key, you don't need to use this pubin tag, you can remove that. And now you need to input your private key which you have for yourself. So I would say private key.pem. Now I want an output, and the output should be called as original message or decrypted tag message.txt. Now if you enter, this is going to create a decrypt message.txt file. Let's view the content of this file. So type in the name of the file, decrypt message.txt, and it comes out as the original message, hi, good morning. So these are the steps. So first we have created private key. We extracted the public key out from that. Our sender will try to encrypt his message using our public key, and then we will be able to take that cipher text and decrypt it using our private key and retrieve the original message. So that's it, guys. That's how you do encryption and decryption in using RSA in OpenSSL. Now if you want to see the difference between these two files which we have, you can call in diff and specify the message, the decrypted message, with the original message which person B has sent. If there's a difference, it would call out the difference. Since there's no difference between these two files and it's exactly the same, it hasn't given any output. Next we need to see what is a hashing or a hash algorithm. A hash algorithm is a one-way function which turns a useful message to a total gibberish. So it doesn't make sense to compare hashing with encryption, since hashing does not relate and is not familiarized with the concept of using a key. The algorithm itself will try to make your information to gibberish without a key. So there's no concept of using a key. The most commonly used hash algorithms are SHA, also known as SHA, or the ones which you see below, etc. But once you do a hash, it is still possible to extract partial or fully unhashed information from a hashed garbage through the use of a large collection of hashed words, phrases stored in some databases. Like encryption variants, hashing algorithms also have their own set of variants. You have 256-bit, 128, 64, 32, etc. How is hashing useful? It is used at places where you don't want to expose or store sensitive information like a password in a database or an external server. So next time when you log into your familiar website, understand that the password you pass to this website server does not validate in its raw form. And now there are some few websites which uses your browser to hash your password before letting it travel across the internet on its way to its destinations. Let alone put aside the HTTPS encryption which happens on the top of that. Encryption, on the other hand, can be used anywhere, everywhere. It is not set by any bounds. You can encrypt information in your own personal devices, source code, scripts and programs, APIs, money transactions, and more on your day-to-day basis. Now let's try implementing a hash using OpenSSL. So we use OpenSSL, same like how we did it in our previous examples. So type in OpenSSL DGST tag SHA-1. So that's the algorithm variant I was talking about. So tag SHA-1 and the message you want to hash. Here the message I want to hash is in message.txt, which is hi, good morning. So if I type enter, this is the hashed value. This value cannot be reversed. If a user has this value, he could not make a guess of what the original text might be unless he has a list of collection of values which he has collected in his past. Now if you want to use the variant of 256 SHA, then go ahead and type in OpenSSL DGST SHA-256 and call in your message which you want to hash. So this has resulted to a hash which has hashed your original message with its 256-bit variant. So that's how you do hashing using OpenSSL. Now if you want to view the different operations which OpenSSL supports, you need to just type in OpenSSL and just call in help. So here we have the list of operations which you can perform through OpenSSL. So we have the standard commands where you have the cipher, digest, public key cryptography versions, the gen RSA tags, gen P key tags which we used in our OpenSSL RSA encryption. We can see the version of the OpenSSL. If you want to do, these are some of the hashing algorithms which OpenSSL operates on. So we have SHA-1, SHA-512, SHA-256, etc. We have MD5. Now under the encryption commands, so this part is dedicated for the hash, and under this we have the list of encryption algorithms we can use. So we have AES 128 CBC, AES 256 CBC, ARIA, and we may have Blowfish, Camellia, DES, RC5, etc. So that's all about hashing and encryption. Hope you like my content. So next time we will check about how HTTPS works and what is a certificate authority. We will see the working description of it. Please subscribe to my channel if you like my content. Bye.